So welcome to our session on cross-platform interoperability for scalable computing and open science analysis and algorithm development. So my name is David Maroney at the Jet Propulsion Laboratory, and I'm also the project system engineer for the multi-mission algorithm and analysis platform, which is a joint open science platform jointly between ESA and NASA. And so we have some of the NASA side of the team in the room today, presenting a little bit on that. You're also going to hear about the Earth Code reproducible science platform, and you'll hear also about standards and best practices on cross-platform interoperability via portable algorithm packaging and scalable workflows. You'll also learn about applications of FAIR principles to these workflows, opportunities and capabilities provided by OGC standards, the OGC API, and Common Workflow Language, also known as CWL. And at the end of this, so there will be 6 speakers, all presenting on these technical topic areas. And at the end of that, there will be about 20 minutes reserved for a Q&A panel discussion. So we've got 3 speakers that are connecting remotely, that'll be presenting remotely, and we've got 3 speakers in the room as well. We've got the chairs set up for the panel discussion for folks in the room. We've got a portable microphone. What I'm going to ask, because we're short on chairs, so Amy actually couldn't join us today. Amy has a flight going back home today. So what I'm going to ask is when we get to the Q&A session for the folks in the room, we've got a portable microphone. For folks who want to speak on that, you're welcome to speak on it. We've also got a Slido poll for submitting questions on Slido. We'll get to that in a moment. But I'm going to ask for folks in the room to please pass the mic around to fellow colleagues in the room just to facilitate that if you could. I also want to acknowledge, I already mentioned Amy Barciauskas. I also have co-organizers Hook Hua and Sujin Shah, also from JPL and from the MAP project, and they'll be speaking here as well. And so what I'd like to do to start off is if you could either use your mobile device if you'd like, or you're welcome to use whatever device you want and enter in the URL manually, or you can use the QR code with your camera. And this should take you to the Slido poll that can start us off with getting a feel for who you are. Now, this is going to be fully anonymous, so you're not going to enter your names in here, but we do have a collaboration notes document. So I'm just going to pause here for a moment for folks to get onto this. Doug, you're going to be blocking the panel discussion. I'm just
kidding. I'm ready. I wasn't sure. I didn't want to press it.
Okay, no worries. All right, so hopefully everybody who needs it has it. We're gonna go back to this. I'm just gonna, okay, one more second. So I just want to remind folks, we've got 2 QR codes on the intro page as well. So the top left QR code will take you to our session page, which the reason why you're here in the room is probably because you found the session page, so that's good. But we also have a QR code that takes you to our collaborative notes document, which we're all welcome to co-collaborate on. The thing I would ask if you could do first, though, is enter in your name so we know who's here. There's an attendance portion at the top of that, name, affiliation. You don't have to do this, but you'd be encouraged also to put your email address there. And in case you'd like to collaborate with us, we can reach back out to you for collaboration purposes. So once again, for folks who just walked in, this is the QR code that takes you to our starter poll for Slido, just to kind of get a feel for who you are, what your interests are, what you'd like to get out of this session. Okay, and then once again, this is a reminder of our agenda. So again, QR code will take you to the collaborative notes document. And in case you're having difficulty accessing the collaborative notes document, it should be associated with the email address that you used to register for the meeting. So whichever email address that corresponds to. Okay, so without further ado, we'll go ahead and introduce our first speaker. Let me get the slide deck loaded. Okay, so our first speaker is Gérald Fenoy, who's the CEO of GeoLabs in France and chair of the Zoo project. So Gerald will be presenting on advancing interoperable geospatial workflows using OGC API processes with the CWL. Okay, Gerald, take it
Thank you
away.
very much. Thank you, David. So hello everyone, I'm Gerald Fenoy from the Geolabs company, which is a French SME that provides support and expertise on the Zoo project and the MapMint SDI. Next slide, please. Our presentation will start with an introduction of the Zoo project. Then we will move to a short presentation of OGC API processes, specifically the part 1 core standard and the part 2 deploy, replace, and in-deploy draft specification. We will then introduce the support for deploying containers and executing them on HPC. Finally, we will present the CWL encoding for Earth observation application package. Next slide, please. Let's start with the Zoo project. When starting the project, our initial goal was to create a software that would allow us to use any open source software or library uniformly. Next slide, please. You can access the official website using the QR code. The Zoo project is an open source server implementation of the web processing service version 1 and 2 and the OGC API processes part 1 core standards. Last year, it graduated as a Node.js project and as an OGC reference implementation for WPS2 and OGC API processes part 1 core. It comprises multiple components, so I won't go in deep details, but I will just introduce them, the concept. The Zoo kernel, which is the heart of the system, which is implemented in C and C++, and it can load and execute any services on demand. Services can be implemented in various programming languages, such as C, C++, Fortran, Java, PHP, Perl, Ruby, Python, C#, JavaScript, or R. A Zoo service consists of an execution unit to be run, which can be a shared library in C, for example, and a metadata file that define all the supported inputs and outputs. The Zoo kernel supports the automatic publication of the result of your service execution using the map server software. We developed also the Zoo API, which is a JavaScript library running on the server side, which helps to chain services and add logic within the chain. We also integrated with the open source geospatial processing engines, such as Orfeo Toolbox and Saga.js, exposing their applications using the OGC processes standard. So with this addition, we reached more than 700 services available with the basic setup. We also have a support for remote execution using HPC and Slurm scheduler, but we will revisit this later on. Next slide, please. So the Open Geospatial Consortium, the OGC, has provided open standard since its creation in 2004. WPS1 was published in 2007 and was using mainly XML encoding. Next slide, please. With the support of the Linux Foundation, the Swagger specification was started back in 2011, and the version 3 of the Open API specification was released in 2017. Next slide, please. OGC embraced the Open API and started to move from service-oriented to a resource-oriented paradigm. Next slide, please. The OGC APIs cover a wide range of standards. I will focus only on OGC API processes, but just want to introduce this concept, illustrating it with the OGC API features. The OGC APIs are provided as different parts that create each aspect of the standard. The part may be in various states, and server may or may not implement them. The OGC APIs are modular and can be combined as building blocks to create more global API. Next slide, please. Combining them together, obviously. So the OGC API command part 1 core standard define 5 requirement classes that we organized in 4 blocks. First, it says that any server implementation should provide a landing page from which we can access the landing page itself, the API definition document, and the conformance information. About the conformance information, it lists all the requirement class supported by the server implementation. This way, the client application is aware of the available server capabilities. The encoding block defines 2 requirement classes defining that the endpoint can be accessed using JSON or HTML format. The Open API, to conclude, requirement class informs that the client that an Open API definition is accessible through the /API endpoint. Next slide, please. About the OGC API processes core standard, it defines how a client application can interact with a server to execute processes. The endpoint defined in the core requirement class on the left are the processes list, the process description without format predefined, process execution, job status, and job result. Then you have the OGC process description requirement that defines a schema for the process description. The callback requirement lets the client pass dedicated parameter in the execution request body to ask the server to invoke a callback at a given state, successful, failed, or during the execution of a job. Finally, the dismiss requirement class defines how to cancel a job run. Next slide, please. Here you are a few screenshots of the basic HTML user interface provided with the OGC API processes implementation from the Zoo project. We used the callback mechanism with the WebSocket to ensure the up-to-date status showing properly during the job execution. We also present the map server HTML UI because since map server 8, it gives the capability to expose your data as OGC API features. On the right, you can see the Swagger UI, which is simply used as the API's documentation. You can access the UI presented there using the QR code at the bottom left, which was developed during testbed 17. Next slide, please. So this slide should have been removed, but I did not do. It simply shows that the Zoo kernel can be split into two parts, a front Zoo kernel and a Zoo Fast Process Manager, or FPM, which enhance reliability of our solution. Next slide, please. So the common workflow language is an open standard for describing how to run processes and connect them to create workflows. A process is an operation that transforms input into output. The OGC published in 2021 the best practice for Earth observation exploitation for Earth observation application package. That defines the best practice for packaging and deploying Earth observation applications encoded in CWL in an exploitation platform. You can access engineering as a best practice using the QR code on the bottom left. Next slide, please. In addition to these best practice documents that we were talking about earlier, OGC is working on a draft specification entitled OGC API Processes Part 2 Deploy, Replace, and Deploy. DRU. It defines the three operations without enforcing any specific encoding in the core. For interoperability purpose, recommendations are made to support at least the OGC application package encoding you can see that is presented on the right. It has two components, the process description corresponding to the process description you can access from the process ID endpoint, and an execution unit, which is an element that should be run. With the CWL requirement class, client can use CWL encoding directly to manage their processes. Next slide, please. In the GeoSuite project, we added support for remote execution of Orfeo Toolbox application on HPC back in 2017, relying on Slurm scheduler directly using the Zoo project and using WPS2 at that time. Then in Fidias HPC, we started the implementation for invoking execution of Singularity container on HPC. Next slide, please. Last year, during the OGC testbed 19 activities on HPGC, high performance geospatial computing, the Zoo project was used to deploy and execute tasks remotely on HPC using the OGC API processes part 2 draft specification and the OGC application package encoding. You can see on the bottom right an execution unit example, and on the top of it, the additional parameter we should use to define the input and output bindings. This notation is obviously implementation specific, drastically limiting the solution's portability. Next slide, please. Sorry. The Zoo project is involved in the Earth Observation Exploitation Platform Common Architecture project led by ESA. In this configuration, the Zoo project under the codename Zoo Project DRU can be used to deploy CWL workflow and execute them on a Kubernetes cluster or HPC. You can actually consult the latest news on the EOEPCA project website about this HPC support. You have a QR code on the top right corner within the image on the right. Next slide, please. Here you have an overview of how the deployment and execution happened. The client requests to deploy a new process by sending a CWL document. The deploy service will parse this CWL to generate the process metadata information based on a service template, cookie cutter, to create the code required to execute the process. Obviously, the application package in CWL is also stored at the same location. At execution time, the deployed process combines the execute request body content and the CWL through the Zook Alrician runner to effectively execute the workflow on the Kubernetes cluster. Next slide, please. As a conclusion, the Zook project is a generic and polyglot processing platform. Polyglot in the sense that it is able to handle multiple programming languages, but also natural languages. The common workflow language provides a generic and reliable way to store and execute workflow on multiple platforms. Earth observation application package allows the process to be moved to the data. Next slide, please. I think this is it. Yeah. Thank you. I hope I was on time almost. Yeah.
Just about a minute over.
Thank you.
Okay, thank you, Gerald. So just to remind folks, or in case it wasn't clear earlier, we will be taking questions at the end during the Q&A session. And just to reorient folks who may have stepped in the room, we have a starter poll. Let me just reload this real quick. And this will just kind of get us familiar with kind of the makeup of the folks in the room, what you would like to get out of the session. For the remote folks. I don't think we need to do it now, though. Do we need to? Yeah. And then also we have a Q&A poll. So I probably should have pulled this up earlier, but you might want to preload this as well, because in case you have a question as we go along, you can actually fill your question in this Q&A section here in advance, and that way we can just queue everything up for the Q&A session. Question in the back?
Just on the polls, is there an active poll? Because I only see the thing.
Does anybody else have any issues accessing the previous poll? It should be active. All you see is Q&A?
Yeah. There was an active poll.
It's not there now. Okay, let me see if I can unlock that. Meanwhile, maybe I could ask Sujin to drive the next speaker here.
You want to introduce the speaker?
Yes. All right, and then so our next speaker is Francis Charette-McNaught, Senior Software Developer, Computer Research Institute of Montreal, Canada, presenting on perspectives on the integration of OGC standards to improve interoperability of open science data processing workflows. And again, once again, Francis, just want to confirm, you'll be sharing your screen, correct? I think, Francis, you might be on mute. Okay.
Yes, I will be sharing my screen.
Okay,
so you can see it.
1 second, I'll just stop sharing on our side. Yes, we can.
All right. Hi, everyone. My name is Francis Charette-McNaught from the Computer Research Institute of Montreal. And as was mentioned, I will be presenting some perspective on the integration of OGC API standards to improve the interoperability of open science data processing workflows. So for our roadmap, I will be presenting a quick overview of the OSPD OGC initiative and the algae bloom use case that was used for this initiative. Then I will follow up with how OGC API processes and CWL were used for deploying this use case. And finally, how they could be used in Galaxy to perform cross-platform workflows. So let's start with the OSPD. So here's a QR code for the Open Science Percent demonstrator if you want to have more information about it. So the OSPD consists of addressing open science for three main goals, which are the reusability, the portability, and the transparency. And the reason for that is that we want to enable better and faster Earth science research. We want to make sure that there's a higher adoption of Earth observation results that can be used, and ensure that there's an increased impact on society. So how can we achieve all of these goals is through the integration of open data, so that any scientist or user that wants to explore the workflows can replicate them using open data, provide some interoperable service operations. So using, for example, OGC API processes and CTRL, so that they can be run in a platform independent way, and offer some visualization tools so that users that are not familiar with all the intricate detail of each API can naturally develop workflows in a visual fashion. So the use case that was selected in OSPD is the algae bloom, which is used for water quality assessment. The area of interest that was selected is presented on this image. And using this area of interest, the idea is to obtain these kind of results, which are indices calculating chlorophyll A, cyanobacteria, and turbidity, which are commonly used to detect the presence of algae bloom. So how we went on to create this data processing workflow is using, as a reference, the OGC best practice for Earth observation application package, which there's a QR code if you want to have more information on that. And this engineering report tells us how to apply common workflow language and OGC API processes part to deploy, replace, and undeploy to basically provide a workflow through the OGC API interface. And it also gives us a lot of details regarding the metadata that is relevant to ensure that open science can be achieved, that we can find the relevant information about who created the workflow, how it was created, and where we can find additional resources. So to the right, we can see a small portion of this workflow that was created for the algae bloom, and a visualization of what the overall workflow looks like. If we dig deeper into the workflow, we can find the definition of the inputs. So in the top portion of the image, the inputs that correspond to the inputs I presented in the previous slides. So there's an area of interest, a time of interest, and some relevant search filters so that we can find data on the Open Data Copernicus platform. Basically figuring out which Sentinel-2 imagery can fit our use case and area of interest. Then there's a process denoted by the S letter on in the middle of the workflow that basically perform a scattering step. So for each of the imagery that was found on the Copernicus workflow, it starts the whole processing pipeline to perform the chlorophyll A, cyanobacteria, and turbidity indices calculation. And for each of these indices, there's a raw data computation, a color map representation, and a graph plot that is presented so that the scientists can analyze the algal bloom detection. The scattered process that was denoted by the letter S itself consists of a sub-workflow that is in itself 3 different steps. The first one is to retrieve the Sentinel-2 imagery from the catalog Copernicus, and the selection of the relevant band depending on which calculation is being performed and with the specific resolution. So I won't give you all the detail, but specifically for the turbidity use case, we can see on the right that specific bands are selected, which are used for that specific calculation. Then there's the calculate band process that involves the relevant calculation for each of the 3 indices to compute. And finally, the plotting process that perform all the visualization step to analyze the results. So once these definitions were defined using CWL and basically be able to be executed on any PC, we were able to deploy them using OGC API processes. So for the use cases, what we did is that we used two platforms. The first one developed by Crim using the Weaver project, which is available on GitHub. You can follow the QR code for the reference code implementation and documentation. And that service is hosted on our Hirondelle platform. And at the same time, we also use the GeoLabs Zoo project that is hosted by the OSPD GeoLab instance. And the deployment of the Sidwell using the OGC API Part 2 deployment is simply to pass directly the Sidwell file. So this can be done in two ways using Weaver. There's a terminal CLI client, and there's the Python client that can be used. So once these processes were deployed and offered through the API provided with the OGC standard, we could move on to the Galaxy platform and perform cross-platform workflows. So Galaxy is a visualization web platform that allows us to string together some piece of different components coming from different processing pipeline and servers. So what we did is that we use one tool that was developed to connect to our Crim server Hirondelle, and the other tool that was used for connecting to GeoLab server, all interacting through OGC API processes. And from the point of view of the Galaxy workflow, it's completely transparent that Sidwell was involved behind the scene. It's all interacting through OGC API processes. So here we demonstrate a part of the workflow where the first the selection of the bands for the turbidity calculation are performed on Crim servers and then shift off to the GeoLab server to perform the relevant calculation to demonstrate the interoperability aspect of the workflow. When executing that workflow, we can see that each steps that are that were defined gets called. So starting from the bottom, the Copernicus portal is requested to find relevant bands. Then the bands of interest that match our search criteria are found. They are selected and hosted through the Hirondelle platform, and then sent to the GeoLab server to perform the band calculation relevant for turbidity in this case. And the obtained image corresponds exactly to the imagery that was presented completely at the start. So if you want to have more information about this workflow, don't hesitate to use the QR code on the top right. It's fully open, it's accessible, and you can try to interact with it and see how everything is implemented. So lessons learned from this work is that we were able to easily share and easily reuse and define an open science workflow simply because they were powered by the native Sidwell and OGC API process interoperability by each platform. Without this, it would have been much harder to do this transition to Galaxy that was basically seamless. Using the Earth Observation application package with Sidwell and OGC API processes, we were able to easily reuse and develop extended tools on Galaxy, and this was this allowed us to demonstrate that execution across multiple servers, although they are implemented completely by different projects and different organizations, can be chained together very easily. And finally, the experiments could very easily be replicated across the different servers. Thanks to the flexibility of Sidwell, it's easily adaptable to many use cases, such as when we were developing at the start the retrieval of data from Copernicus up to the plotting and more scientific aspect of the pipeline. And because of this flexibility, we were able to easily deploy the processes on whichever server that is more relevant for the operation. So this brings opportunities to deploy processes close to the data and therefore make more efficient use of data access and computation. Thank you.
Thank you, Francis. Okay, so in the interest of time, we'll just go right into our next speaker. I'm gonna reshare. Okay, so our next speaker is Sean Wilkinson, who's a research scientist at the Oak Ridge National Laboratory. We'll be presenting on the FAIR principles for computational workflows.
Thank you. So, yes, I'm probably going to tell everyone at least partially something you've already heard, but hopefully something new in the middle of it, right? The FAIR principles, obviously, and workflows, we all do probably both of those. But as a quick personal background, I'm not actually an earth scientist. I have a background in bioinformatics. I did a postdoc with high energy physicists. I've been at the Oak Ridge Leadership Computing Facility for the last 5 years. This is a picture of me with Frontier, which is the fastest computer in the world. But we do all kinds of different science on it. Not everybody's aware of it, so that's why I mention it. But nowadays I do cancer research, and I'm the co-chair of the WCI FAIR Workflows Working Group. I am excited to collaborate with y'all. That's why I'm excited to be here and hopefully work more with earth scientists. So anyway, what are computational workflows, right? Everybody knows, but they don't know, right? It's a deceptively hard question. A few of the choices are that it's a program of programs, often directed acyclic graphs of tasks, like up in the top right, you see that's what workflows are often depicted as, but what a workflow is. The mathy people will call it a composition of data transformations, but the truth is no one actually knows. We're all using them anyway to automate our science. This in itself is an interoperability problem, makes it difficult to talk about workflows because we're all talking about them a little differently. So the easier question is why computational workflows? And we all know a lot of this too, right? But it's to manage complexity, the automation helps avoid human errors, such as leaking data that didn't belong in that place with those people. The workflows enable to use the right tool for each task instead of writing one big ugly program. And they enable expert optimizations, which is particularly useful for scaling, right? Because workflows, if you're using a good workflow manager, it will help you allocate and schedule resources automatically, error handling, task restarting, all kinds of nice things if you're using a mature system. Obviously, it helps improve scientific practice. The more that you can automate your experiment, allows you to repeat your experiment easily, reproduce results, and it allows others to reuse part or all of your computational methods for their own experiments, so they don't have to reinvent the wheel. And this is the most important part of workflows to me, is the automation aspect of it. And so as we add automation, we always add complexity to things, but does complexity have to increase from a user standpoint? Can we actually make it simpler for the user? Obviously, on the right, you see this guy with the self-operating napkin. It's a Rube Goldberg cartoon. My favorite part is the spoon in the bottom left flipping a cracker to distract the parrot. This is what workflows feel like to me a lot of times, is really, really just stitched together madness. But when I ask must complexity increase for the user, an interesting question is who will be the user? So traditionally, humans have been the programmers, right? Always. Increasingly, humans and machines are writing code. We're using things like Copilot, right? Eventually, machines might be writing an awful lot of code. It's definitely coming. Autonomous workflows are sort of a higher form of automation, but they're going to require a lot of groundwork. And surprise, the FAIR principles actually are laying that groundwork and have for 10 years. So this quote here, FAIR data are essential to the future of human-made collaboration, or human-machine collaboration and autonomous machine-to-machine communication. This is really crucial. A lot of people, when they hear the FAIR principles, they think data, which is great, but it also extends to other things because overall we're aiming at autonomous workflow type things. So obviously the FAIR guiding principles, everybody's probably familiar with it. They're published in 2016 by Mark Wilkinson, who's no relation to me. They listed 4 main emphases, with findability, being able to find your workflow, being able to access it using open protocols and that sort of thing. Interoperability, once you have found, I'll probably just talk about workflows, data. So being able to find the data that's well described, being able to access it over open protocols, being able to interoperate with it and make use of it once you've found it, and then reusability is largely about licensing. Are you allowed to use it? And being clear about that. But all of these are strongly emphasize metadata for enabling machine actionability. And I specifically, just this one sentence that I call out here is distinct from peer initiatives that focus on the human scholar, the FAIR principles put specific emphasis on enhancing the ability of machines to automatically find and use the data, in addition to supporting reuse by individuals. And that's an important piece that people often miss, is this has always been designed for enabling machines to do these sorts of things. Then there was a working group that further extended these for research software, and their work took a couple of years. They published in 2022, Michelle Barker and others. They're slightly different for software because software is executable and it's made of components. So there's a few extra principles in it. Then the way that they apply the principles is a little bit different. So if you're not familiar with this, I recommend taking a look at it. It still emphasizes metadata strongly for the same reason, which is machine actionability. This is where we come in our working group. We are working on applying them to computational workflows, which are they're subtle and weird. Like everyone in the room will have a different definition for workflow and everyone is correct. That's the problem. So how do you apply principles to something that's so nebulous as that? Workflows can relate to FAIR as data if you're treating the source code as data files, for example. But workflows are executable. They're software. They're also instruments of FAIR, and what I mean by that is that they can be used to verify, your data. You can use workflows to make things more fair. They're intimately tied to the ecosystem in which they exist and run, and they are compositions of objects which themselves can be fair. There are also reasons to extend FAIR because workflows are not fully described by FAIR and that sort of thing. But ultimately, and I have in the bottom right, autonomous workflows that read and react fundamentally depend on machine actionability. So, of course, machine actionability depends on metadata again. Humans and machines are similar because without proper metadata, they're just guessing. So these large language models and things like this, it's all based on probability. But with proper metadata, they can make informed decisions. The same things that enable machine-machine interactions also enhance human-machine interactions. So it's not a lot of fun to look at things like the RO crate that I have to the right there. It's just long and tedious and boring, but it's worth it if we can make the machines do it for us. So what is machine actionability? I have these two different quotes here from two different papers. The capability of computational systems to use services on data without human intervention, and also the capability of computational systems to find, access, interoperate, and reuse data with none or minimal human intervention. That's obviously sounds almost exactly like FAIR, right? But there's common language in the two of them. And so if you combine the definition, you can say that machine actionability is the capability of computational systems to use and reuse data with minimal human intervention. I say use and reuse because they are actually different. It is actually possible to make things that are reusable, according to the definitions for FAIR, for example, that are not usable in a practical sense. And I love discussing that sort of topic. I just can't hear. But if you look more closely, even there's the three main parts of this: the computational systems, data, and human intervention that we're trying to minimize. This is everybody who does work with a computer. So the FAIR principles aren't really just for metadata. They're for everything. They're for all of us who are doing these. And I'm sure I'm preaching to the choir on that. But everyone's not always aware of all the different places that FAIR has been applied, which at this point, data, software, there are people who looked into doing it for open hardware, artificial intelligence, machine learning. We're working on it for workflows, and there's also facilities and instruments, which is a particularly interesting way of looking at things because, so this came from a workshop last September, but the focus is on the assignment of persistent identifiers to research facilities instrumentation so that, for example, when you know where your data came from, you know exactly which microscope made it, exactly which whatever was sensed. But that's useful from a workflow standpoint. We can program with that. We can track data that wasn't quite right. We can figure out why it wasn't right, but we can also connect the facilities and instrumentation. That's particularly important in what the Department of Energy is doing right now with the integrated research infrastructure efforts, where we're trying to connect all these different facilities, some of which are like light sources, particle accelerators, these sorts of things, but connect them to supercomputers that are geographically distinct. And so we have all these different efforts that we're trying to undertake to connect these. I'm just going to talk a little bit about the one at the top left, just to show, because the ACE testbed, basically we have this computer that we're trying to test all these different kinds of processors, GPUs. We've got graph processors. There's multiple kinds of fabric there for networking, multiple kinds of storage. They're completely different. The yellow is actually a Kubernetes infrastructure for containers. These are all connected with different kinds of networks and everything else. That part's not impressive. The part is just that this is hard. This is hard to even keep track in your head of what all of this is. It's a test bed, so it's always changing. So even as of January, it was all of this madness with these different nodes, these different kinds of processors. I can't keep it straight in my head at all. I think the only person who can is Ross Miller, who made this slide originally. And I shouldn't have to, right? If I'm doing workflows, I should be able to, hopefully someday, be able to ask, is there a computer available that is suitable for my work that I'm trying to do? Is it available? Is it on? Is it is there capacity on it right now? And to do that, it would be really nice to have an API to program against, which the Department of Energy has been working on quite a bit. Our facility API that we're doing is based on the one at NERSC from Berkeley Lab, where the goal there was to make everything callable, to make all the computers be able to check your quota, be able to move data around and everything else completely through an API. And this is really great. Obviously, like that's why the top level, you can connect all these different facilities programmatically. You see in the middle there with the facility API, workflow and data streaming orchestration. Ours is still under construction. And so what it feels like to me is that we are connecting the railroad right now. And so that's what this is a picture of connecting the railroad, which I think happened in Utah. This is where they connected the East and the West. But it's going to feel really happy. See, they all have champagne and things. It's going to be great when we get there, but we're not quite there yet. We're still working on that part. On the other side of the railroad, though, it's going to be things like Workflow Hub, which is already available. It's a workflow registry that helps you fare. And so you can see, I don't know how, I guess the text is okay on this. I'm not calling out these features specifically to say, look at all the things it can do, which are great. What I'm particularly trying to show is that in the bottom left, the Seek ID for use with Seek API, all of this is callable. And if it's not callable, it will be. So all of these things that you would like to be associated with your workflow, you'd like to be able to work with and know about, but callable from an API. This is a registry that is free to use. It is not about hosting your workflow. It's about registering what you already have with it. And it's quite useful, actually. And so then finally, because I'm not sure how much time I have left, but I highly recommend people take a look at the original poster and then the paper that followed for 10 simple rules for building fair workflows. Because to make truly fair workflows is not really possible. It's an aspirational kind of goal, but this is a really simple set of things that you can do that help towards that. And so then ultimately, in summary, the FAIR principles are not just for metadata. Applying FAIR to every level of the ecosystem will help enable computational workflows that handle scaling issues automatically someday and maybe even self-assemble. And hopefully the Terminator and that sort of thing will actually happen when we do that. So acknowledge my funding and thank you very much for your attention.
Thank you, Sean. Yes. All right, we'll transition to our next speaker. So our next speaker is Garen Smith, who's a software architect with Telespazio, affiliated with ESA, and he's based in the UK. And Garen, I'll just go ahead and drive. I believe that's what you wanted.
Yes, please. Thank you, David.
Sure.
Thank you. So hello, I'm Garen Smith, a technical architect working for Telespazio UK. I'm going to talk about an ESA project called EarthCode, which relates to reproducible science. I'll also talk about how EarthCode is influenced by EWEPCA Plus, workflow and data standards. EWEPCA Plus is a set of building blocks and standards supported by ESA that can help implement platforms and services. The aim of EarthCode, or the EarthCode project, is to help users create scientific workflows for their experiments and publish them to a repository after they've been verified, so that experiments can seamlessly be reused with the specified data and necessary infrastructure according to FAIR open science principles, engaging with the relevant communities to further science. During the presentation, I'll be talking about the ESA strategy, major use cases, the conceptual architecture, workflow metadata standards. I'll be looking at ODC-OPO processes, OpenEO process graphs, and other workflow solutions, and the use of open source software. Next slide, please. So the ESA EarthCode vision will support the scientific community to create and exploit science experiments or workflows. It will do this by reusing existing platforms that allow science workflows to be developed and also executed. It may be that workflows are developed on one platform and then executed on another platform near the data, and with more resources. There are two roles, or major roles, within the project. The science contributor will conduct and publish the initial experimental workflows along with the experimental results. This may be done in collaboration with other scientists, and once published, the scientist user can use FAIR principles to find, access, interoperate, and reuse workflows and results. This may include viewing experimental descriptions and experimental results, reproducing experimental results from a published workflow, reusing a workflow with different inputs or different configuration, maybe using a GUI, and then changing a workflow to create a new workflow. Publishing is also supported, and EarthCode will allow scientists to publish workflows and experimental results. In terms of storage, EarthCode will also allow scientists to store input data and experimental results to allow scientific work to be preserved for the long term. And for ESA, we'll use the ESA NOR, or network of resources, will provide the funding mechanism for scientists to get credits or sponsorship for using the EarthCode platform or resources. Next slide, please. We can summarize the two main roles and the use cases associated with these roles. EarthCode will support the science contributor role with the following use cases: access to compute resource on the cloud, support to develop workflows, support to execute workflows and conduct the science associated with them, support to publish workflows and workflow experimental results, and finally it would allow interaction with the wider community using the Open Science Catalog, and we'll talk about that more in detail later. EarthCode will also support the science, previous slide, thank you. EarthCode will also support the science user role using FAIR principles with the following use case: find workflows and experimental results, access workflows and experimental results, then reuse the workflows with experimental results. And this will be enabled by using interoperability provided by the open standards that we'll describe later. By doing this, the science user role can continue to develop the cycle of community collaboration. Next slide, please. EarthCode will be implemented using 3 work streams. Workstream 1 will provide capability for one or more platforms to host workflows with a large amount of compute capability near the data. Workstream 1 will send experimental outputs or products to GitHub so that they can be published to the Open Science Catalog when authorized. Workstream 2 will provide the capability for one or more platforms to help develop workflows. Workstream 2 will send experimental workflows to GitHub so that they can be published to the Open Science Catalog again when authorized. Finally, Workstream 3 will develop a science user community based around the artifacts published to the Open Science Catalog. Through Workstream 3, the science user community will help guide EarthCode's evolution. Next slide, please. We can now consider the standards that support EarthCode implementation and interoperability. OGC API records will be used to represent metadata that describes workflows and provides a reference to the workflow implementation. This may include the workflows themselves, the experimental config that uses the workflow, and also the applications and dashboards that provide a human interface to both the workflows or the experiments themselves. OGC API records is recommended by EUEPCA Plus and also supported by the EUEPCA catalog building block. And that means that it's easy to ingest and also to discover using the catalog. Next slide, please. Stack will be used to represent metadata that describes product metadata or experimental output, and also input metadata or experimental input. Stack again is recommended by EUEPCA Plus and supported by the EUEPCA catalog building block, again making it easy to ingest and also to discover. Next slide, please. OGC API records can reference different types. Previous slide, thank you. OGC API records can reference different types of workflow. This could include process graphs with OpenEO, which again is supported by EUEPCA Plus, CWL with OGC API processes, again supported by EUEPCA Plus. In some cases, basic code types that do not implement a formal workflow, such as Python, can also be referenced. That doesn't mean that Python is not capable of implementing a formal interface, just that sometimes it may not. Note the workflows can also reference source code, which will allow access to the underlying source code to allow potential code changes to be made. Scientists should also not necessarily be familiar with workflow standards or workflow formats. Therefore, a key success criteria to Earth Code is to support scientists convert their code into a recognized workflow format without much pain, hopefully. Next slide, please. ESA are keen to support collaborative open source development. Earth Code will be built using open source software. The EUREPCA Plus open source is already open source. It's available now and growing. Earth Code open source catalog also uses the EUREPCA Plus catalog building block and also the EUREPCA Plus harvesting building block to allow data to be ingested and shared. And some Earth Code components are already live. So the Open Science catalog is now live with the URL available above. And the Earth Code portal which is now a placeholder for platform integration over the next 12 months and beyond. And that's now live already. Next slide, please. So in summary, ESA's Earth Code aims to bring existing platforms together into a single open access solution for ESA scientific activities. This is done using open access cloud-based development environments and leveraging on federated EO platforms. Thank you for listening.
Thank you, Garen. All right, so our next speaker is Hook Hua, who's the MAP project system architect and from JPL, so take it away.
Thank you, David. Everybody, I'm going to be talking about some of the key lessons learned in one of our projects called the MAP project, which is a collaboration between NASA and ESA. And in continuing with today's themes, particularly some of the things that Garen and the previous speakers mentioned, we'll be hitting a lot of the similar highlights, but it'll be very interesting to see some of the nuances and differences and particularly the lessons learned. I wanted to first start off by kind of just conveying that the context of what the MAP project is mostly focused around biomass analysis. And I wanted to convey intentionally here, on the left and right-hand side are data products that the joint MAP projects use. But on the left-hand side are data that's really hosted on the NASA side, and on the right is data that is hosted on the ESA side. But part of this collaboration project is actually how do we utilize both assets, and that whole data locality, data migration, all of those considerations for those things. On the left, you see mostly spaceborne LiDAR data sets, as well as SAR-based data sets. A lot of this in the context of biomass, mostly, like height of vegetation, canopy heights used for above ground biomass estimation. Similarly, on the right, you've noticed there, we've included NISAR and we've included biomass. So those are the two really big and important missions that hopefully will launch next year, but that will be added to the analysis that the science team members of the MAP projects will be using. In this example here are some of the algorithms that the ESA side have been using. One of the things that we wanted to point out is that on this MAP project, on ESA, they mostly are using these platforms to mature algorithms that are used for the production environment for the biomass mission. So in essence, it's less so of the analysis, but more so of actually developing, maturing, and then promoting these algorithms to their production environment. Similarly, though, but a little bit different, is on the NASA side, most of our use cases so far has mostly been around, how do you take the products already sitting in an archive center, things like at NSIDC or LPDAC and Oak Ridge, or an LDAC, and how do we take those and generate other higher level products? In this example here, Laura Duncanson and her team have actually used this to generate, they've scaled up their analysis in MAP. I think they ran it to like about 4,000 parallel multi-core nodes, be able to generate these global scale. For here in this example here, they use ISAT2 to fill gaps in the JEDI's above ground biomass estimation products. So it's like a global map, but all generated using algorithms developed on the map and then generated on the map itself. So there's definitely challenges in all of this. I'm probably preaching to the choir, right? There's data locality issues that we saw with the whole ESA NASA data. There's data access. How do you address the idiosyncrasies of, do you do Earth Data Cloud? Do you do ESA? What about on-premise, right? There's a lot of these things. What about data management? There's a whole slew of interoperability aspects that we're going to touch upon, or at least you're hearing a lot today. There's sharing as well, which is another aspect of this joint map. How do you actually share data that you generate? How do you share code? How do you collaborate? I mean, it's very mundane, but it's actually quite challenging. Lastly, but not least, also is large scaling. So this is one of those unique aspects of map, which is how do you take the algorithms and go beyond just the analysis and into an actual global processing, a multi-scale, decadal scale type of processing. In a nutshell, MAP is really, it's an acronym that stands for Multi-Mission Algorithm and Analysis Platform. And it's really kind of addressing all of the things that I just mentioned, right? It's got the data access, it's got the infrastructure, the processing, and also how do you handle the code, the artifacts, the workflows, the algorithms, the repeatable algorithms, and also the gray matter, the intellectual assets, the knowledge that we get from sharing. In essence, when we talk about map, and Sujin's going to talk a lot more in the details of map next, by the way, we're actually talking about two map instances. We have a map on the NASA side, and we have a map on the ESA side. On NASA, we deploy that and run it on our baseline AWS environment. But on ESA, they actually have been running it on the Orange Cloud, as well as something new called Cradius, which is an Earth Science specific hosted cloud platform. So a lot of the challenges is really about how do you actually collaborate and connect these two systems together and make it work in a more seamless way across the different user bases. One of those key things is really that you may be wondering, how is this different from like Pangeo or some of the other platforms, right? One of the nuances that we've seen is that Pangeo is actually really good for like highly fast and really iterative DAS-based analysis, right? Multi-core. But when you get to this point where your algorithms, like on the ESA side, are mature, and you want to take these algorithms and actually run it in a production crank to do like, multi-decadal scale product generation analysis. This is kind of like where that sweet spot of where MAP comes in. And I think Sujin's going to dive into details about a lot of the underlying standards and interoperability that will be used for that. I wanted to show one example here though. This is an example from one of our collaborators. I think she's at UMD. Her name is Niha Hunka. She has actually been using MAP to do biomass harmonization, and her team actually has been doing really great work in high impact harmonization for these type of above ground biomass harmonization, these intercomparisons. And one of the things that she told us was that before MAP, it used to take her 2 weeks to generate one intercomparison, to do one set of runs. Now she said she literally could go get a cup of coffee, come back after lunch, and the entire intercomparison is done. So that type of rapid speed is really good because it allows you to kind of make fast and iterative and actionable science. And that's kind of like one of those key takeaways about the impacts of large scale processing capabilities. You can see here on the right, though, there is a part of this environment. It's more than just a Jupyter Hub. It has integrations with other plugins. In this example here, there is a QGIS type of integration. You can see it's embedded in the same environment. There's other examples that Sujin will show as well. I'm going to be preaching the choir here that you've heard a lot of the prior talks talk about all the various standards. OGC is not the only standard, but it's definitely one of the more popular standards here. For today's talk here, for my talk here, I'll be focusing on the OGC standards relevant for algorithms, processing, and also orchestration. That's kind of like one of the overall themes of this session. We wanted to convey, though, that the key 3 artifacts that we're dealing with, at least for this talk, is going to be about a lifecycle transition states of where the users are interacting with code when it's sitting in like a GitHub repository. Then they're going to collaborate and share. But eventually, they're going to want to build some binary reproducible package, right? It's not just a Docker container, right? Turns out OGC has a standard for that, right? We've heard bits and pieces called the OGC application package. But that's just the package. We can then take that package as part of a life cycle and actually deploy it into a processing system, like similar to what Garen just mentioned, right? About you can deploy it to different processing clusters, whether it's HPC or in the cloud or whatnot. But that's in a life cycle context, that's in an executable state. And part of that is actually the realization that of all of these artifacts in these lifecycle states, it's actually correlated with different elements of these platforms. One being like, there's an interactive algorithm development environment. Then there's the actual catalogs that could catalog these application packages. So you can actually search for data, but you can actually search for reproducible algorithms. You can actually do similar things with like Zenodo, for example, right? We've heard already many projects doing similar things like that. Last thing on the upper right is an OGC application deployment execution service. Basically, it's like a processing cluster, right? But it's abstracted away. Right? Underneath it could be an HPC, it could be Amazon, it could be Argo, it could be Kubernetes, right? It could even be Lambda, right? But the point is that there are standards for that. So in a nutshell, though, Sujin's going to dive deeper in this, but we basically have a unified joint architecture design where on the left-hand side, you have the NASA elements, and on the right-hand side, you have the ESA elements. We share the same architecture, but we actually have very independent implementations, but there are standards involved, highlighted in the purple lines there that you see that represents the OGC interfaces. But the core of it is this collaboration where we have shared code bases, shared stack catalogs, but also what we're working on is a shared joint algorithm catalog as well. And these OGC standards are kind of central to that. But we've learned a lot over the years. One of which is that we learned that OGC standards typically sometimes only go so far in the real world use case. Like when we, in an academic setting, everything is fine. But when we actually deployed it and actually use it in real production, we found that, we've learned a lot. We've learned that sometimes for our needs, there are certain things that we didn't really need in OGC. There are certain things that OGC was very, very good at in terms of establishing a baseline. But for some cases, like we had use cases in a real world production where we wanted to extract real-time analytics, metrics out of our processing. And there's no spec in the current OGC baseline to do that. So yeah, we can work on extensions or we can work on, but that's the point, right? How do we deal with that jointly, right? You can have side APIs, or do you establish a baseline where we, at minimum, we jointly agree on meeting the OGC, but everything else is in addition to that? Or do we work with OGC to add, additional, amendments? These are the questions, right? Another key lesson we learned is that I believe there was a few previous talks that mentioned about best practices, right? Some of these OGC specifications are not standards, they're best practices. Because they're best practices, it's a little bit loosey-goosey in terms of how you can interpret that. So when it gets down to, when it gets down to the implementation, you have to make real choices. And so being a best practices, it leaves some room for interpretation, really. And so, going from before in this previous slide here, we initially thought, oh, the OGC application package, we need an application descriptor, we have this, we have to include stage in and stage out. Do we use papermill? A lot of the OGC engineering test beds use papermill, right? But it turns out after iterating with our ESA colleagues that it could actually be a lot simpler than that. That a lot of the examples we saw in the engineering test beds were actually just part of the best practices type of recommendations, or it's optional, right? In the end, we jointly agreed on a much more simplified approach and was still in compliance with the best practices. And so in the end, it was just, you have a container, whether it's Docker or Singularity or Podman, and a simple C to the L. And at minimum, that's all you need. And Susan is going to dive a little bit deeper, but that's kind of like the key takeaway, right? What is that basis set and what is that agreement? One of the other things we learned is who should have responsibility for stack handling, right? Stack is great, when you talk to a computer scientist, but when you talk to user, they don't want to deal with this, right? Can we automate the generation or handling of stack is the question, right? One of the things that we learned on the mission side is that in the missions, we decouple the metadata and stack and all of the data management away from the algorithm developers. And so the question we're raising is, how much should algorithm developers need to handle in terms of stack? Should the responsibility lay in the algorithm developers, or should it be laid in the, say, the platform folks, right? It's one of those key questions. The other key takeaway also is that as part of the stack handling as well, is that it should be decoupled from the algorithm core. So in essence, what we've learned in our collaboration is that we want to decouple algorithms from data management. And we can do so by this integration of how an application package integrates, or how it gets deployed into an OGC ADIS, as they call it, right? The processing clusters. Effectively, we want to let the processing clusters do the data management and let the algorithms focus on the actual core algorithmic handling. And if we expand it further into like orchestration, and there's like OGC EMS and other orchestration management, we found that in addition to all these services, that old saying, program to interfaces and not to software stack, right? That's a really old saying. But that's one of those key things, is that we started with that. We said, oh, we're going to stick with standards. Everything's going to be fine, right? But it turns out that after a while, we started developing convenience wrappers around these OGC standards. Like, oh, well, instead of making 5 lines of calls to a REST interface, let's wrap that up into a one-liner. Well, that's great. But now with the code calling those one-liners, it makes it a little bit harder to be portable across different platforms. So it's just one of those key lessons learned, right? Do you stick with standards, or do you have convenience wrappers, or do you just say, well, let's just all use the same stack then, right? But these are the questions that and the challenges that we're encountering, right? My last slide here is really more about that data locality, right? Going back to the very first slide, right? On the left-hand side, you've got all the NASA asset data. On the right-hand side, you've got all the ESA data, including like Copernicus DEM data as well, right? And, I've circled there that, for the NASA side, we're mostly in Amazon US West 2 in Oregon, right, with Earth Data Cloud. All the data is co-located. The NASA map platform is co-located. ESA is doing something similar in the EU region, but they're not in Amazon, right? So it's like, well, if ESA needs to access NISAR data, for example, NISAR is expected to generate 70 to 80 terabytes a day, per day, right? And so that's a lot of data. And so who's going to pay for all of this egress, right? Pulling data out of NASA will cost money, right? Whether Estes is paying for it or the map platform is paying it, somebody still has to pay a bill, right? How do you minimize that, right? So there are options for something called requester pays, where, if ESA gets an Amazon account, they can pay their own egress. Or if NASA gets an Orange Cloud account, we can pay for our own egress. But the issue is that there are policies that prohibits NASA from buying Amazon and ESA from buying Amazon and NASA from buying Orange, for example. So this goes back to those OGC standards, right? With things like the application package, it's just one extra standard or best practices that could help in making our code and assets and workflows just a little bit more portable. And with that portability, we could kind of realize, that process migration over data migration, meaning that we can take those algorithms, and ESA could take their algorithms and run them on the NASA map and vice versa. Although, the reality is that we're basically punting the data migration cost to a processing cost problem. But that's a separate discussion for another day. And I'll end with this. This is just the key takeaways of what I presented today. It really boils down to collaboration, sharing, processing, as well as the slew of things that we mentioned in the last few slides about interoperability and portability. That's it for my presentation. Thank you for your time.
All right, thanks so much, Hook. Our next speaker, Sujin Shah, who's the Map Platform Manager at JPL. And Sujin will be presenting on the utility of standards and best practices for interoperability on open science platforms, not just map. Take it away.
Hi, everyone. I'm Sujan Shah. It's fun to be the last speaker when most of your content is already covered by all the other speakers. So hopefully I can do justice to bring everything back as summary and having to real-time pivot based on what I'm going to talk today. And Hook, I can't dive any more deeper. I think I'm done. All right, so let's see. What are open science platforms? Like, we've heard the term open science. So open science platforms is essentially platforms that can enable users and scientists to, collaboratively develop, share, and run their algorithms at scale, adhering to the open science principles of transparency, reproducibility, accessibility, and being inclusive. Platforms should also provide infrastructure to do this amount of large scaling using open science principles. One of the examples that I will cover today is the map platform, which you've heard from Hook, and I'll focus on something that should really matter, which is the OGC application package that you've heard in multiple presentations today. And why should these platforms be interoperable? We saw from Francis and Gerald as to how they are using multiple different deployments of different institutions, and they're talking to each other using open standard. So it enables collaboration. It enables reproducibility of results by users on one platform and trying to reproduce the same thing on another. And it also is efficient in terms of reducing the amount of duplicate work that software teams need to do to develop these platforms by reusing of these tools. So just summarizing the key best practices that anyone out there who's planning to maybe develop a platform is ensure data accessibility, follow standardized data sets, provide clear documentation and metadata around that data, use a service-oriented architecture. So we see a lot of these OGC APIs, they're all REST-based processes. So, have an open API spec for your API so that if a machine is talking or a human, they can really, read your documentation. Web services also allow you to be modular and scale, be highly available depending on your use case. Probably you can also use Docker as a containerization application so that you can quickly deploy, redeploy, and scale up, and adhere to certain metadata standards. And we've heard this from the previous presentations, but these standards are more not for your data, but also like when you are responding to an HTTP request, like you should probably not just come up with your own way of responding, follow some standards and document it essentially. What are standards? Essentially, they are established protocols that ensure systems can interoperate. Sometimes they are not very easily human readable, but they are meant for machines and tools to interoperate. And they provide like common language for exchange of information. We've heard about OGC. Again, that's not the only standard, but something that MAP has chosen to adopt partially. Some of the standards that from OGC we implement on MAP is the Web Map Service, the Web Processing Service, WPS, you heard that in the previous presentations, and the OGC best practices for Earth Observation Application Package. Now, that's something that I'll dive deeper into and why you should care about it. Overview of the map, you heard this, won't go over. It's a joint platform by NASA and ESA. And this is something that was not shown earlier, which is the life cycle of a user on the map platform, or essentially any platform, would be to come in and do some algorithm development, iterate, test, and then be ready. Once you're mature, you go into data processing. You would want to probably scale up to a global scale, and then catalog all your outputs and do visualization and analysis on these outputs. And all of these things are communicating using open standards and APIs. So what enables us is all of these are now modular. You can plug and play any service for visualization or cataloging as long as that particular tool or platform follows these open standards. And that's one of the key takeaways. So we saw this diagram earlier about the architecture of the map. I will talk about the application package and why you as an algorithm developer or a scientist should care about writing code and adhering to the application package standard. So what is the OGC application package for Earth observation? It's essentially a framework that standardizes the deployment and execution of geospatial applications, right? It includes guides for how to package, how to write metadata so that it is interoperable and reproducible, right? So why is it important for you as a scientist or you as an algorithm developer? Well, it makes sure that your code is interoperable. You can run on like different platforms and systems. It's not just it works on my laptop. It's reproducible, so other people from the community can validate your outputs by executing it on a different environment. It's easily shareable. You can just share a link with your pre-built package so that somebody doesn't have to really dig through your documentation. It's consistent so that running it again, you would always have the same output and not worry about, oh, well, this operating system is now, changing their libraries and how should I install your package? That was, something that you had created 5 years ago. So it kind of hits that point and it's efficient. It saves time. Someone's not building an entire software stack just to reproduce your outputs. So this is how it looks essentially. There is your process, which is the code that you write and compiled in a container. It could be Docker, Podman, Singularity, any container. And then write a small CWL file, which is essentially the application descriptor that defines what the inputs are, what the outputs are, and any other software requirements that this process, the image, might have. That is our application package. Now, the big question is, when you are wanting this to be interoperable, how do you communicate inputs and outputs, especially when they are like geospatial data? Well, stack was the answer when we were developing this. You can have a stack catalog directory coming in and a stack catalog directory going out. You can see one of the advantages of doing this is you can construct a workflow from using OGC application packages, and I'll show later on we did that. So what is CWL? It's yet another YAML. It is essentially a YAML file that declares, we have a Docker image. Where is my built process? It shows you inputs. Now, the key, you could have like string, int, boolean, directory. It takes care of constructing the right input, providing prefixes and all of that. And then you have an output. Some of the standard input types that we are using from OGC APAC are there on the OGC website, but it's like all your primitive data types. But the key here is the type directory is used to denote a stack catalog. So whenever a user defines directory, it's assumed to be a stack catalog. That's what the best practices document says. So let's see, what's the key advantage of building an application package for the user? Well, one, you can develop it locally, run it locally by having your application package and then stage inputs and outputs. But how do you run it locally? Is it a Docker run command, or what is it? So for that, we have CWL tool, which is the reference implementation of the CWL workflow. And then you provide your process CWL, which is the descriptor we saw earlier. And then you provide your inputs, and this is as simple as it gets. And any other user who wants to reproduce this just needs to call this, because the process CWL has the link to the Docker image. So they don't need to build any code. All they need is CWL, maybe some space and resources on their laptop to reproduce a single output. Now, the next question is, well, yes, it works on my laptop. It also works on Jupyter Hub. But do I need to change my algorithm to run it on the cloud? Do I need to say, parallelize my code or something? No. I think that the key advantage of using the OGC application package is even on the cloud, the platform is running the same CWL tool. So you have your application package, you have the inputs, you still have your stack going in and out from directories. But what the platform provides is it adds a stage in step, which converts any remote URL. So when you are running it on the cloud, you're not going to provide directory as an input because you don't know where your code is running. You don't know the directory structure. But what you can do is provide a URL to the stack item JSON once you have searched the stack catalog for your input. So the platform would add the stage in step to essentially download those remote stack catalogs, provide them as a directory, and then once you produce your outputs, it would stage them out and publish them to the stack catalog. This ensures that the user, the algorithm developer, doesn't need to do more work to run their code on a platform in a scalable manner. It's the same code and the same package, the same executable that is running. And this is the job on the cloud. What we have done on the map is we've worked on this blue application package builder, which is kind of, I wouldn't say the reference implementation of the OGC best practices, but something that jointly ESA and NASA are agreeing to use. It can be imagined as a GitHub action, for example. That's where we want to be. Right now, it's just the simple code we run on our CI/CD. But the key is that we take in inputs from different modes of a user. So we don't want the onus of writing the CWL to be on the algorithm developer. What we have done is we have created a simple UI. It's a form, you fill in, you put in your inputs, you add your files, you say this is the script I want to run. This is where it is. Provide the link to your GitHub repository. We will do all the building. We will write the CWL. We will package the container and then publish it to a registry. One example is to publish it on Zenodo. Now, I'll get into that. We've always heard Zenodo as something where you could put your GitHub URL and get a DOI. You could put data as an artifact. But what we want to do is promote executable code or executable environments as an artifact. We did that on one of our projects where we published products and submitted not only our products, but our workflow and this OGC application package to the ORNL DAC, which then published them on Zenodo. Now here, it's too small probably, but on the Zenodo link, you can see we have a tarball of our Docker image where you could download the tarball, you can download the CWL and reproduce the exact same result. And that's checking off the boxes of interoperability, reproducibility. It's easily sharing. You can go on the link, just download it. It's consistent. Everybody can download it and it'll give you the same output. It's efficient, not spending time in building the whole software stack yourself. So I guess in conclusion, we can see why interoperability, OGC standards, and primarily the application package is of great importance to you as an algorithm developer for collaboration and credit for reusability. I think that's it. I think that's my time. Thanks.
All right, so as we transition to the Q&A, I'll ask the speakers in the room to come up to the podium. I was going to have them sit there, but we only have 2 microphones in this room, so this will make it easier. And then before we do that, I'm just going to reorient folks to our Slido polls. So this is the ending poll. The ending poll is now active. You're welcome to now use your smart devices to get to the QR code to do the ending poll. Just give a moment for that. And the Q&A poll is also active, so you're welcome to continue entering questions. We got a few questions in already for that. And just to remind folks, I see a lot of people did sign in on the collaborative notes in the attendance section, so thank you so much for doing that. Again, if you want to collaborate with us, please also feel free to include your email address on that as well. All right, so this is, once again, this is the Q&A QR code. And I'm actually just going to leave this here for now, or should we pull up the poll itself? What do you guys think? Sure. Or just read the questions out loud?
Just have the questions out loud.
Okay, so the first question, and this is actually these are all anonymous, is we have a hard time incentivizing scientists to write high quality metadata for data sets. How will we incentivize them to publish their workflows? So also, I'll allow folks, the panelists that are in the room, to speak first to that, and then anybody that's remote, the panelists that are remote, you're welcome to speak after. So whoever wants to take that first.
So I had shown about Workflow Hub, which is a registry for putting your workflows on and everything, but it's also it's designed to help carefully track who made it, derivative works that came from it, that sort of thing. Like the only ways that I know to incentivize people is either to punish them and make them like, you have to do it because of funding, you can't have money, or else like you'll be famous and everyone will love you. And so that's the approach I like better, right? The carrot. But yeah.
I would like
That's an intriguing point. So I see Katie was like, I can also comment that we encounter this a lot, and not just the map, but many of our other projects as well, especially on the mission side as well. I mentioned earlier that one of the things that we've been doing is to kind of decouple that responsibility, meaning that can we lower the bar of entry? We probably can't eliminate it, but can we lower the bar of entry for particularly the science community, right? What's the minimal amount of metadata that they need to curate? Ideally, if their data products that they are generating are self-documented, so to speak, right? Could we auto-generate stack? These are some of the things that we discuss across many different projects. Could we also just make it, what is the minimum amount, right? What is the basis set of fields that's absolutely required for discovery, for example? So there's some things, I don't think it addresses fully the entire issue, but definitely we could lower the bar of entry.
And for the panelists that are on remote, does any of
Yes.
the panelists
Yes.
have a comment?
Well, in the end, for most scientists, the end goal is to publish their paper and get citations. So if you can have a way to publish your workflows and increase the chance of reusing their work, so therefore increasing the chance of citation and referencing, that's a great way to incentivize them. And for a scientist, the main challenge is to use these platforms or these complicated standards, and the best you can do is to make it as simple as possible for them. If it can be transparent how to use this platform, moving from a Jupyter notebook directly to a deployed workflow, that's the best way to help them.
Okay, thank you, Francis. So in the interest of time, we'll just move on to the next question. So the NASA ESA collaboration on MAP is impressive. Do you anticipate buy-in from other space agencies such as Japan, India, etc.? I'll let either Sujin or Book take that one first.
I don't think we should get in trouble. Maybe Katie, if you want to start.
So hi, Katie Baines, NASA Earth Data Officer. So several of these things are a result of work that has been funded by my program and collaborations we've had with specifically our European partners in a bilateral sense. At this point in time, I don't think that we are expanding the collaboration to have yet another sort of either Japanese or Indian instantiation of the MAP. So I think that Hook did a good job of sort of looking at the bilateral nature of the collaboration, with our ESA counterparts and with NASA. What we are looking at doing is expanding the people we invite into the fold to participate and collaborate in the development of these workflows and like collaboration, but instantiating yet another map is not something that is on our roadmap. I know that's like sort of probably not what you wanted to hear, but we are interested in expanding the collaboration, but not the instantiation of these efforts at this point in time. Just because it's been a real fruitful collaboration, but it takes a lot of expensive care and feeding to sort of work through the issues just in a bilateral fashion. And if you add another node to that graph, you've got a lot of like edges to create to get all computer science done.
All right, thank you for that question, and thank you, Katie, for that answer. Appreciate that. All right, so our next question is from the Slido once again. So actually, we have it shared on here. I understand the benefits of CWL. Were there any challenges that had to be overcome in the course of these use cases?
I think one was training the user. Like some users want to know more detail about how their code is being run. So like making the user understand what CWL is and how it instantiates processing services in the backend. That was one challenge, and also something that our user was interested in learning. So that was like, oh well, I know how to run my code using Python or R, but now CWL adds another layer, which then changes how you actually write the interface to your script. Most of the times, users are like, yeah, all I need is a config file. Just give me a YAML and I'm done. Well, OGC application package does not allow you to just have a YAML file sitting anywhere. Well, if you explicitly define your inputs with the types, then you can, have a archivable inputs YAML file that we can store and reproduce later on. So like having users rethink the entry point into their algorithm was one big challenge that we had to overcome with a lot of these developers.
Does anybody remote have a comment on that?
Yeah, I'd add that my experience is that CWL is a great implementation mechanism to achieve an ends to a means, but most scientists aren't particularly interested in the nuts and bolts of CWL or OGC API processes. So providing support for them through, I think there was some talk earlier on about the the Map OGC application builder. So anything that can support scientists to produce either stack or CWL is really helpful. Thank you.
So I wanted to further add on to this as well. I kind of second that. When we first worked with CWL, I think we were probably asking ourselves like, oh my goodness, this adds a lot more complexity to the system. Is this really, really needed, right? And I liken it to be like that old computer science book. You guys know, but remember that old Gang of Four book they say, right? The computer science Bible, right? Anyways, the overall theme of all of those design patterns in that old Gang of Four book is hide what varies. And I feel like, in many sense, CWL is that consistent way to hide what varies. And so I think, at first it was just like, there's so much complexity in this. But once you understand what it's trying to do and what the benefits it provides, you can kind of see why CWL is actually in a lot of the OGC engineering testbeds and reports and reference examples.
So I actually have a question about CWL. So I think that, and this is just out of ignorance, I think that there are a million ways to sort of to traverse a directed acyclic graph, like a DAG, right? Like you could do a workflow, but CWL seems to be sort of just the winning currently DAG YAML. So do you see other sort of workflow engines? I know that there's Airflow, there's Orchestrate, or there's like every startup has their own. Are you seeing adoption of CWL by those workflow engines? I was Googling it, and Amazon's something or other is also now supporting CWL. Is this something that we should start looking at as not just a implementation, but something that is actually implemented by lots of different? Does my question make any sense? Like, are you seeing this as a place where we can actually sort of say, no, you're going to do CWL, and it'll work on all these different platforms? Maybe that doesn't make sense to the question.
So, through our collaboration with ESA, what we found out is, look, so CWL is the description of your workflow, right? There are many ways to run that CWL. Like, you don't need to use CWL tool, which is the reference runner. So, like, I think Airflow also supports CWL. Argo also has. So ESA is using Argo. They have written a converter to convert CWL into an Argo workflow. So CWL is not something you run, but you describe, right? So that's the workflow description language. And then CWL tool is their reference, what we use. Yeah.
Cool, thank you.
Last comment. So common workflow language, at least at our computing center, we have enough trouble getting people to use workflow systems themselves anyway. But CWL doesn't show up too much in high performance computing yet. There's a working group for it to extend CWL to be more suitable for HPC, but I don't use CWL, but my understanding is that there's certain places where it is lacking for certain kinds of dynamic workflows that are not already spelled out, they're not DAGs, and also for certain kinds of iterative AI feeding into modeling and back that may struggle with CWL at the moment.
That's very helpful, thank you.
Okay, so we do have to close this session out. We're eating into the coffee break, but I'm going to invite the panelists on Zoom, on remote, to do one last closing comment. Whoever wants to go. Okay, so in that case, let me just show one last slide here. These are our key takeaways. Let's see if I can reload this. So this is in draft form. This is the disclaimer, still being drafted, but this is what we have at this point. I kind of tried to weave together the key things from all the different topics and speakers. So hopefully this does it justice, but we'll keep drafting this. I'll set up a meeting offline with the co-presenters and the co-organizers, and we'll try to finalize this slide deck. But at any rate, thank you all for joining. You're welcome to hang out, chit chat with us. We'll be here. So thank you all.